In this second video on Unit 8, we're going to look at a few more identities. So far we've looked at the reciprocal trig functions, the cotangent identity, the tangent identity, and the three Pythagorean identities. We're going to add a few more today. First of all, the negative angle identities, or sometimes they're called the odd-even identities, are going to deal with what happens if we look at an angle and its opposite. And we've actually looked at this before. So think about if we had a situation, say we have a unit circle again, and if I think about rotating an angle of theta as opposed to rotating an angle of negative theta. And think about what points we would have. If this is on the unit circle, so this point over here would be the point -1, 0. If we're on the unit circle, this would be a point, we could call it arbitrarily xy. This would be 1 unit out. Likewise, I know my circle is not very good, but this would also be 1 unit out down here. And this xy coordinate down here on the unit circle would have the same x coordinate. However, its y coordinate would be the opposite of the one that is up in that first quadrant. So we know that the x coordinates are the same, the y coordinates are opposite, and the ratio of y over x would end up being opposite values as well, which takes us to our negative angle identities. And we know that the cosine of an angle will equal the cosine of the opposite of the angle. And we remember the sine and supplement, cosine and opposite, tangent and half turn. We utilized this idea before when we were solving some trigonometric equations. So the negative angle identity for cosine talks about the angle, when we take the cosine of it, and the angle opposite of the angle, and the cosine of that value will be the same. They have the same x coordinates. Now on the other hand, the sine of an angle and the sine of the opposite of the angle, think of the y coordinates here, they're not equal. I can't place an equal sign between them. However, if I make one of these be the opposite, say this one, that will be a true statement that the left side will equal the right side. So again, these two values are not equal. The sine of an angle and the sine of the opposite of the angle, or the sine of the negative angle, they're not equal. But multiply that one by -1 and it actually will be the same as this value. For tangent, y over x versus the y coordinate over the x coordinate, you're going to have opposite values here for our situation. So the tangent of an angle and the tangent of the opposite of the angle, they're not equal. That only works for cosine. It would also work for secant as well. It's a reciprocal trig function. So if I make the tangent of the angle become the opposite sine, then the ratios will be equal. So that's our negative angle identity, or again, sometimes it's called odd-even identities, because even functions will have that reflective characteristic, and these two functions are odd and they don't have the characteristic. Okay, next is the supplements theorem. We remember sine and supplement, and that will have something to do with what we're going to look at here. So again, I will deal with having a unit circle, and if I rotate on the unit circle, have that distance be 1, and I have an xy point here, and this angle's theta. Now, if I reflect this angle over here, I know that reference angle-wise, this is also equivalent to theta, and the measure of this angle will be its supplement. So this angle will be the supplement of angle theta. And I can write the supplements in terms of degrees or in terms of radians. I'll actually do both over here. But this point, when we reflect it over, will have the opposite x coordinate but the same y coordinate. And again, that radius will still be 1. So here's my angle theta, and this angle from the reflecting this over this axis is the supplement of that angle. So I know that the sine of an angle and the sine of its supplement, and I'll write this originally in terms of degrees. So the sine of an angle and the sine of the supplement of the angle will be equal because the y-coordinates are equal. Now, on the other hand, if I take the cosine of an angle and the cosine of the supplement of the angle, they're not going to be the same. The x-coordinates are opposite values. So they will be related, but one will be positive and one will be negative. So if I multiply one of the sides by -1, then they will be equal. For the tangent function, the ratio of these two values and the ratio of these two values will not be the same. So the tangent of an angle and the tangent of its supplement will not have the same functional value. However, they will just be opposite numbers. So if I multiply the 1 by -1, then this statement will be true. Now likewise, I could substitute a pi in each of these cases for the 180 if my angle had been posted in radians as opposed to degrees. So you would not use both. It would all depend on the context of what your angle was given in as an original. So if it was given in degrees, you'd want to have this as 180. If it's in terms of a radian measure, then you'd want to have it in terms of pi, which is equivalent to 180 degrees. Now, the last new identity that we'll look at today is the cofunction identities. The cofunction identities are going to deal with complementary angles. So, if I draw a picture of, again, a unit circle, and I think of rotating and have my angle here, and have this be angle theta, and I'll particularly put it in the first quadrant as I have in the other instances, although it works for any angle measure. This angle that I have in the first quadrant does have a complement. This little angle here would be the complement of that angle. So this angle, if I looked at this in terms of degrees, would be 90 degrees less theta. And if I actually kind of take that picture and take this angle and move it over into its own little unit circle, so taking this little angle and move it over here, so here's theta, this would also be theta up here, and here is that complement of my theta here, so here's my 90 degrees less theta. Now it ends up, I go over x and up y to get to this coordinate, which means if I plop this down in this quadrant, I actually will have this coordinate be over this y coordinate and up x. So I get another kind of interesting situation happening here, that the sine of this angle, which would be this length, is going to equal the cosine of this angle, because it's going to be its first coordinate. I also find that the secant of this angle is going to equal the cosecant of this angle, of my complement, and I find that the tangent of this angle will equal the cotangent of this angle, because the tangent of this angle is going to be the ratio of these two, and the cotangent of this angle will actually be the ratio of the y over x, so these will be equivalent. And that's why these two functions are called sine and cosine, secant, cosecant, tangent, cotangent, because we have their complements, the CO, the complements of one is equal to the other. So the sine of an angle and the cosine of its complement are equal. The secant of an angle and the cosecant of its complement are equal. The tangent of an angle and the cotangent of its complement are equal. So for instance, if I had sine of 20 degrees, that would equal the cosine of its complement, which would be 70 degrees. If I had the secant of 42 degrees, then the cosecant of 48 degrees, its complement would be equal, and so on. So the cofunctions deal with complementary angles. Now on to a few applications. We have number 2 we're going to look at, and then we're going to look at number 3 as far as a proof. So our directions have use Pythagorean identity rather than the reference triangles to find the sine of theta if cosine of theta is equal to 3/4. And we know that we also want our sine function to be something that is positive. So if I think about what does Pythagorean identity tell me, and if I'm dealing with a sine and a cosine function, I know that the cosine squared of an angle plus the sine squared of an angle equals 1 is one identity, Pythagorean identity, that would relate my situation. I know the cosine of my angle is equal to 3/4. I want to determine what my sine of my angle is. So if I do a little bit of algebra here, get a common denominator, I know that the sine squared of my angle is equal to 7/16. So I know that the sine of the angle would be plus or minus the square root of 7/16, which is plus or minus square root of 7/4. Now I did have one additional piece of information that was given to me, and that's that the sine has to be positive. So I know that the answer to my question has to be just that the sine of theta is equal to positive square root of 7/4. I wouldn't want the negative value or the opposite of that value because of that condition being given to me. Now I also know something else is true about this situation, is that if the cosine was positive, the cosine is the x-coordinate, so that would have had to have meant my angle would be a first or fourth quadrant angle. But once I was given the condition that sine had to be positive, I knew that this was the quadrant my angle had to be in, because cosine and sine are positive in the first quadrant. Now I also ask you to find the tangent of theta. And the tangent of theta, I don't necessarily need to go back and use a trig identity to find that, although I could use the 1 plus tangent squared of theta equals secant squared of theta in order to determine my tangent. But I can also use my ratio that the sine of an angle divided by the cosine of an angle is equal to the tangent of the angle from the tangent identity. And since I know that the tangent will, little mistake there, we know that we can take the sine of the angle and divide it by the cosine of my angle, which was given as 3/4. Do a little inverting and multiplying, and we can find that the tangent of this angle, I need some lead here, tangent of the angle will end up being, reducing these 4's down, the square root of 7/3, and it also makes sense that that would be a positive ratio in the first quadrant as well. So sometimes we can do some manipulation with our identities to help us find some different quantities. We never are finding theta. We'd have to use a calculator to determine that from here, but we used our Pythagorean identity and then used a tangent identity. Now the last thing we want to look at today is how do we prove or verify a trig identity. And so these are fun. We're going to look at this first one on number 3. We're going to prove or verify that this in fact is an identity. And the way we're going to do this is I have a rule here, and I claim that this is true for all angles x, that the cosine of x plus the sine of x times the tangent of x will always equal the secant of x. And so we prove that by doing some trigonometric substitutions and or some algebra in order to make the left side be equivalent to the right side. So take the side that's more complicated and work with that to make it look like the other side. You don't have to work with specifically the left side. You pick the side that kind of looks like it needs the most work done to it to make it be this simplistic secant of x. Now, you'll also need to supply your reasons for why you're doing what you're doing. So let's just look at an example. So I want to prove that this left side, in fact, is equal to the secant of x. So I need to do some trig substitutions and some algebra. I'd leave this cosine of x alone. And I can see that over here, I want to do a substitution for that tangent. I know that the sine of x I'll just write down. The tangent I know can be substituted as sine of x over cosine of x. And I'm going to put a little question mark there because I'm trying to prove that they are equal. And I basically will put ditto marks on my right side so I won't keep writing things down for the right side. But we have done a substitution by the tangent identity to get my first step. Now I can see that I have to combine these together, and I know that I want to make the left side equal to the secant of x. I can't multiply both sides of this equation to cancel anything out. What I have to do is just work with one side and don't use any multiplication property of equality. You're just going to work with one side and try to get this expression to simplify down to secant of x. So I can see that I have to get a common denominator. This fraction has a denominator of cosine of x, and this doesn't. So I'm going to multiply this by cosine of x over cosine of x down in this next step. And I'll do a little bit of simplification here as well. Now, the reason I can do that is you could put this as a reason as by multiplying by 1. I multiplied this fraction or this number by 1. You could also call it algebra. So I'm not going to get picky about that. Now, I have cosine squared of x plus sine squared of x all over cosine of x. And I can see that this numerator will in fact end up just being 1. And that's because of the Pythagorean identity. You could add an extra step if you want to write it as cosine squared of x plus sine squared of x all over cosine of x first, but I'd allow you to do that type of a substitution. Once they have the common denominator, you're free to add the tops as long as it correctly can simplify down. Then my last step, I can show that my left side is equal to secant, my right side is equal to secant, and I can have this justification of going from here to here because of my reciprocal identity. So you can do some little shortcut notation for doing your solving. So these questions are very similar to assignment 1, except now your bonus is you actually know what you have to make your expression equal to. So only work on one side. I'm going to have you guys only working on one side to try to make one of the sides equivalent to the other side. We'll do one more real quickly. I have sine cubed of x plus sine of x times cosine squared of x, and I want to show that this in fact is an identity, that this left side of the equation will always be equivalent to the right side, which is the sine of x. So again, I am not going to multiply both sides by anything. I'm not going to divide both sides by anything. I'm going to work with the left side all by itself and try to make it equal sine of x. Now, I see I can do some factoring here. If I factor out a factor of sine of x, I'm left with sine squared of x plus cosine squared of x, and I'm going to put the question mark, equals sine of x. And the reason I can do that is just by factoring. If you call it algebra, that's fine as well. Now this is almost too easy because now I see a Pythagorean identity substitution. And lastly, I actually have multiplicative identity here, that the sine of x, or any number times 1, will give me itself. And that's really by multiplicative identity. Now, if you skipped right from this step to this step, I wouldn't have a problem with that. All right, so there we are, 2 little proofs. Now it's time for you to practice using some of your identities and proving some identities.